The sun is roughly 1,000 times too cold to produce its own light. That is not a metaphor. That is not an approximation. If you calculate the probability of two protons fusing at 15 million Kelvin using classical physics, you get a number so close to zero that it makes zero look generous. 10 to the negative 290. The sun should be a cold, dark ball of hydrogen. Every star should be. The night sky should be black, and your planet should be frozen, and you should not exist. But right now, as you hear this, 4 million tons of matter are being converted into energy inside the sun every single second, because particles are doing something that classical physics says is impossible. They are walking through walls, and the three men who proved this independently within 24 hours of each other in the summer of 1928 were all destroyed for it. One tried to flee Stalin in a kayak across the Black Sea. One was called the weakest link in America's atomic security by a congressman who later went to prison for fraud. One died at 54 in a New York apartment with no memorial service. And the man who actually discovered it first, a year before any of them, lived to 101, and almost nobody remembers his name. Tonight, I want to walk you slowly and carefully through Gamow's kayak on the Black Sea. Gurney and Condon's paper at Princeton, submitted one day later. Hund's forgotten calculations in Göttingen. Marie Curie's intervention at the 1933 Solvay conference. The McCarthy hearings that dismantled two careers. The Attoclock experiments that suggest tunneling may be instantaneous, and the published, peer-reviewed calculation that says the vacuum of the universe itself could tunnel out of existence without warning. Subscribe if you have not, settle in, and stay until the end, because the phrase "the alpha particle" slips away almost unnoticed, written by one of these men in 1928, is going to take on a meaning he never intended, and it is going to be the last line of this story. Let's get into it. Every second, the sun converts 4 million tons of matter into light. 4 million tons. Gone. Not burned. Not consumed. Converted. Mass becoming energy at a rate that would annihilate the entire Earth in about 150 million years if you could somehow feed the planet into the reaction. And the process that makes this possible, the specific quantum mechanical trick that allows hydrogen to fuse at a temperature roughly 1,000 times too cold for classical physics to permit it, was figured out by a 24-year-old kid in Göttingen, Germany. In the summer of 1928, he wrote it up in a few pages. He submitted it to a German physics journal on July 29th, and one day later, on July 30th, on the other side of the Atlantic Ocean, two physicists at Princeton submitted a paper to Nature solving the exact same problem, independently, without ever speaking to each other, without knowing the other existed, 24 hours apart. And the person who actually saw it first, a year before, either group, a quiet German physicist named Friedrich Hund, lived to 101 years old, and almost nobody in the world remembers his name. The kid from Göttingen tried to escape the Soviet Union in a kayak and nearly drowned in the Black Sea. One of the Princeton physicists was hounded by the House Un-American Activities Committee for decades until he was reduced to investigating UFOs. The other Princeton physicist was denied every security clearance he applied for, fired from his university with no hearing, and died of a cerebral hemorrhage at 54 in a New York apartment. There was no memorial service. This is the story of quantum tunneling, not the version you were given, the real one. I spent an unreasonable amount of time reading about this. Not the physics, which I will get to, the people, because the physics is unsettling enough on its own. But what happened to the people who discovered it? is worse. And the fact that this story is not taught in every physics classroom on Earth, that it has been sanitized into a neat little textbook paragraph about wave functions leaking through barriers, should make you angry. Every physics student learns tunneling as a solved problem, a fun quantum quirk, a good exam question about probability amplitudes decaying through potential barriers. Nobody teaches them that the man who first applied it to the nucleus tried to flee Stalin in a kayak. Nobody tells them that one of the co-discoverers was called the weakest link in our atomic security by a congressman who was himself later jailed for fraud. Nobody mentions the man who saw it first, who outlived everyone, and who barely talked about tunneling in interviews because the credit had been taken so thoroughly that even he seemed to have forgotten it was his. Here is what the textbooks do not tell you. In the summer of 1928, a 24-year-old Ukrainian physicist named George Gamow was sitting in Göttingen, Germany, working under Max Born. He was attacking a problem that had been driving nuclear physicists quietly insane for years. The problem was this. Ernest Rutherford had been scattering alpha particles off nuclei since 1906. He had used alpha particles to discover the nucleus itself in 1911. By the 1920s, he had mapped the Coulomb barrier surrounding the nucleus with extraordinary precision. He knew how high the wall was, and in 1927, he published a result in the philosophical magazine that contained a paradox so severe that it should have set every theorist in the world on fire. But it did not. It sat there, in the data, unexplained, for almost a year. The paradox was this: when you fire alpha particles at a uranium nucleus, particles with an energy of about 8.5 million electron volts cannot get in. The Coulomb barrier, the electrostatic wall surrounding the nucleus, is too high, roughly 25 to 30 million electron volts high. The alpha particle does not have enough energy. It bounces off. That was fine. That made sense. The problem was the other direction. Uranium-238 emits alpha particles with an energy of only about 4.2 million electron volts. Those particles are getting out. They are escaping from behind a barrier that is 6 times higher than their energy. That is like watching a tennis ball sitting at the bottom of a canyon spontaneously appear at the top, not rolling up the side, not being thrown, just appearing there. Classical physics had no explanation for this. None. The alpha particle does not have the energy to climb the barrier. It cannot borrow the energy. There is no mechanism in classical mechanics that allows this to happen. And yet it was happening, continuously, measurably, in every gram of uranium on Earth, in every hospital using radium therapy, in the ground beneath your feet. The impossible was happening everywhere, all the time, and nobody could explain it. Gamow saw the answer in days. He had been trained in Schrödinger's wave mechanics. He knew Max Born's statistical interpretation of the wave function. And he realized that if you treat the alpha particle not as a little ball, but as a wave, the wave does not stop at the barrier. It does not bounce off cleanly. It decays exponentially inside the barrier. Yes, it gets weaker, but it does not reach zero. On the other side of the barrier, there is still a tiny non-zero amplitude. And in quantum mechanics, a non-zero amplitude means a non-zero probability. The particle can be found on the other side, not because it went through, not because it drilled a hole, not because it borrowed energy and paid it back. There is no trajectory through the barrier. There is no through. There is simply a probability of being here and a smaller probability of being there, and sometimes there is on the other side of a wall that should be impenetrable. Gamow wrote it up. He submitted his paper, Zur Quantentheorie des Atomkerns, to Zeitschrift für Physik on July 29, 1928. He thanked Max Born for hospitality and Nikolai Kochin for help with the integrals. He was 24 years old, and he had just explained, for the first time in history, how radioactive decay works, the first successful application of quantum mechanics to a problem inside the atomic nucleus. One day later, on July 30th, at Princeton University in New Jersey, two physicists named Ronald Gurney and Edward Condon submitted a paper to Nature. It was titled Wave Mechanics and Radioactive Disintegration. They had solved the same problem, independently, using the same physics, arriving at the same conclusion. They had never spoken to Gamow. They had never seen his paper. They did not know he existed. Think about that for a moment. Two groups of physicists, separated by an ocean, with no communication between them, solved one of the deepest puzzles in nuclear physics within 24 hours of each other. July 29th and July 30th, 1928. And here is the detail that makes it stranger. They were not the first. A full year earlier, in 1927, Friedrich Hund had already described the same phenomenon. Working in Copenhagen and Göttingen, Hund had calculated the quantum mechanical tunneling of particles through potential barriers in his work on molecular spectra. He showed that, in a symmetric double-well potential, a particle can tunnel from one side to the other. He even calculated the tunneling rates and showed something remarkable. A small change in the height of the barrier could change the tunneling time from nanoseconds to 1 billion years. The exponential was that brutal. Hund saw it. He published it. And then Gamow and Gurney and Condon came along with a dramatic application, alpha decay, the thing that made headlines, and Hund's priority was quietly forgotten. 3 discoveries, 2 continents, 1 day apart. And the man who saw it first got nothing. I want you to remember something as this story unfolds. Remember the phrase that Gurney and Condon used in their Nature paper to describe what the alpha particle does when it escapes from the nucleus. They wrote, and I am going to give you the exact words because they matter. Much has been written of the explosive violence with which the alpha particle is hurled from its place in the nucleus. But from the process pictured above, one would rather say that the alpha particle slips away almost unnoticed. The alpha particle slips away almost unnoticed. Remember that phrase. It is going to take on a meaning that Gurney and Condon never intended, and it is going to haunt the rest of this story. Because the same mechanism that lets an alpha particle quietly slip through an impenetrable barrier, the same leak of probability through a wall, is also, and I need you to hear this clearly, the mechanism by which the universe itself could one day cease to exist. Not in an explosion, not in a collapse, in a quiet transition that nobody would see coming. But we are not there yet. We are in 1928, and the 3 men who just cracked the atom are about to discover that solving a problem in physics is the easy part. The hard part is surviving what comes after. To understand what happened next, you need to see who these men actually were, not the textbook versions, the real ones. Gamow was born in Odessa on March 4th, 1904. His mother died when he was young. His father was a teacher. He grew up in a city on the Black Sea that was, in those years, one of the intellectual centers of the Russian Empire. By the time he reached the University of Leningrad, he had fallen in with a group of young physicists who called themselves the 3 Musketeers. There was Gamow. There was Lev Landau, who would go on to win a Nobel Prize and survive being beaten nearly to death by the Soviet secret police. There was Dmitry Ivanenko, and there was Matvei Bronstein, a theorist of extraordinary promise who specialized in quantum gravity. Bronstein was thinking about how to quantize the gravitational field decades before anyone else took the problem seriously. He was 31 years old when the Soviet state put a bullet in the back of his head. But that comes later. Gamow briefly studied under Alexander Friedmann, the mathematician who had derived the expanding universe solutions to Einstein's equations in 1922, the equations that would eventually lead to the Big Bang theory. Friedmann died of typhoid fever in 1925 before Gamow could finish his studies with him. But the seed was planted. Gamow would carry Friedmann's cosmological thinking forward for the rest of his life. The student of the man who discovered the expanding universe would become the man who figured out what happened in the first few minutes of the expansion. Gamow was tall, 6'3". He had an enormous laugh and an accent that people described as a mix of German and Russian, with something else entirely that nobody could quite place. He was known for practical jokes that walked the line between brilliant and genuinely irresponsible. Years later, when he collaborated with his student Ralph Alpher on a paper predicting the relative abundances of hydrogen and helium left over from the Big Bang, Gamow added the name of Hans Bethe to the author list. Without Bethe's knowledge, purely so the paper would be authored by Alpher, Bethe, and Gamow. Alpher, Bethe, Gamma. He then suggested that his other collaborator, Robert Herman, should change his last name to Delta to complete the joke. Herman declined. Alpher was furious. It was his doctoral work. The Alpha Beta Gamma joke ensured that everyone remembered the pun, and nobody remembered that a graduate student had done most of the actual physics. Gamow thought this was hilarious. Alpha did not speak to him for years. But in 1928, the jokes were still years away. Gamow was a young man in Göttingen who had just solved a problem that Rutherford himself could not solve. He had arrived in Göttingen in the summer of 1928 on a fellowship from the Rask Orsted Foundation and had gone to work under Max Born, who ran one of the 2 or 3 most important theoretical physics groups in the world. Born had invented the probabilistic interpretation of the wave function just 2 years earlier. Schrödinger had published his wave equation in 1926. The tools were fresh. The paint was still wet on quantum mechanics. And into this environment walked a 24-year-old from Leningrad with an idea about alpha particles. The paper he wrote in Göttingen solved the problem in a few pages. It is elegant in the way that correct physics tends to be. No special assumptions, no ad hoc hypotheses, just the Schrödinger equation applied to a charged particle inside a potential well surrounded by a Coulomb barrier. The wave function leaks through. The tunneling probability depends exponentially on the barrier parameters. The Geiger-Nuttall law falls out naturally. 17 years of empirical data explained in a single calculation. And he was about to return to a country that would not let him leave. Gurney was English. Born July 1st, 1898, in Cheltenham. He had earned his PhD at Cambridge under Rutherford himself, which means he was trained by the very man who had identified the paradox that tunneling would solve. In 1928, he was at Princeton on a Proctor Fellowship, working with Condon. He was quiet, careful, deeply physical in his intuition. Neville Mott, who would share a Nobel Prize in 1977, later wrote an obituary for Gurney in Nature. The line that stays with me is this. Mott wrote that Gurney never trusted mathematics. No theory was a theory to him until he could grasp it intuitively and, above all, draw diagrams of it. Here was a man who would not believe an equation until he could see it, until he could make it physical. And that instinct, that need to feel the physics rather than just calculate it, produced one of the most beautiful sentences in the history of nuclear physics. The alpha particle slips away almost unnoticed. Condon was American. Born March 2nd, 1902 in Alamogordo, New Mexico. I want you to hold that birthplace in your mind, Alamogordo, New Mexico, because 43 years later, in 1945, the first atomic bomb would detonate at the Trinity test site 60 miles north of where Condon was born. The man who helped explain how the nucleus works was born in the desert, where the nucleus would first be weaponized. That is not a metaphor. That is geography. And geography in the 20th century had a way of catching up with physicists. Condon grew up poor. His father was a construction engineer who moved the family frequently. Condon educated himself largely from library books and entered the University of California at Berkeley, where he earned his PhD in 1926 under Raymond Berg. His dissertation was on the intensity distribution in band spectra, which led directly to the Franck-Condon principle. The Franck-Condon principle describes how the probability of a vibrational transition during an electronic transition depends on the overlap between the vibrational wave functions of the initial and final states. It is one of the most widely used concepts in molecular spectroscopy. Condon derived it at 24, the same age Gamow was when he derived the tunneling theory of alpha decay. 24 was apparently the age at which theoretical physicists in the 1920s did their best work. After his PhD, Condon spent time in Göttingen and Munich, absorbing the new quantum mechanics from its creators. He returned to Princeton in 1928, where he joined the faculty and, with Gurney, cracked the alpha decay problem. His career after that was a nearly unbroken arc of achievement. He was prolific. He gave physics the Franck-Condon principle, the Slater-Condon rules, the Bright-Condon theory. He would go on to become the fourth director of the National Bureau of Standards, president of the American Physical Society in 1946, president of the American Association for the Advancement of Science in 1953. During the war, he worked briefly at Los Alamos as an associate director, though he left after just 6 weeks because he clashed with the security apparatus. Even then, before McCarthy, before HUAC, Condon was allergic to the idea that science should be conducted under surveillance. He believed that open exchange of ideas was not just a nice principle but a practical requirement for good science. That belief would cost him everything. He was, by any measure, one of the most accomplished and respected physicists in America, and none of it would save him. But before the destruction, there was the discovery. And the discovery itself, the actual physics of what Gamow and Gurney and Condon found, is stranger and more consequential than any textbook has ever communicated to you. Because quantum tunneling is not a curiosity, it is not a fun quirk of the quantum world. It is the reason you are alive. It is the reason anything is alive. And I mean that literally. In a way, I am going to make very specific. Let me walk you through what actually happens when a particle tunnels. And I am not going to simplify this, because the unsimplified version is the version that matters. In classical mechanics, a particle is a thing with a definite position and a definite velocity. If it is moving toward a wall and does not have enough energy to get over the wall, it bounces back. End of story. The wall wins every time. No exceptions. This is so intuitive that you do not even think of it as a physical law. It is just how objects work. A ball rolling toward a hill that is too steep rolls back down. A car driving toward a ramp that is too high does not make it to the other side. The energy budget does not balance, so the crossing does not happen. In quantum mechanics, The particle is not a thing with a definite position. It is described by a wave function, a mathematical object whose squared amplitude at any point tells you the probability of finding the particle there. When this wave function encounters a potential barrier, something happens that has no classical analog. The wave function does not stop at the edge of the barrier. It does not reflect cleanly. Inside the barrier, in the region where the particle classically cannot exist, the wave function does not oscillate. It decays. Exponentially. It drops off. But, and this is the critical point, exponential decay does not mean it reaches zero. If the barrier is thin enough, or if the energy of the particle is close enough to the height of the barrier, a non-zero piece of the wave function leaks out the other side. And on the other side, the wave function starts oscillating again. There is a finite probability of finding the barrier. The particle did not go through the barrier. I need to be clear about that. There is no trajectory. There is no path that starts on one side, passes through the interior of the barrier, and emerges on the other side. The question, how did it get through, has no answer in standard quantum mechanics, because the question assumes a trajectory that does not exist. There is probability on this side. There is probability on that side. There is decaying amplitude in between. That is the entire story. The barrier is not a place the particle visits. It is a region of probability decay. And on the other side of that decay, reality continues. This is what Gamow calculated for the alpha particle inside a uranium nucleus. The alpha particle, 2 protons and 2 neutrons bound together, sits inside the nucleus held by the strong nuclear force. That force is attractive, but very short range. Beyond its reach, the alpha particle feels the repulsive electromagnetic force of all the other protons in the nucleus. This creates a potential barrier, a wall of positive charge. The alpha particle does not have enough energy to climb over this wall classically, but its wave function leaks through, and the rate at which it leaks, the probability per unit time that the alpha particle will be found outside the nucleus, depends exponentially on the width and height of the barrier. This exponential dependence is ferocious. A small change in the energy of the alpha particle produces an enormous change in the decay rate. Gamow showed that this exponential relationship is exactly what the Geiger-Nuttall law describes. The Geiger-Nuttall law was an empirical observation, known since 1911, that connected the energy of emitted alpha particles to the half-life of the radioactive isotope. Hans Geiger, Rutherford's former student and the inventor of the Geiger counter, and John Mitchell Nuttall had noticed that when you plot the logarithm of the decay constant against the energy of the alpha particle for different radioactive isotopes, the points fall on a straight line. Each radioactive series, the uranium series, the thorium series, the actinium series, produced its own line. The relationship was beautifully clean, and it was completely mysterious. Nobody knew why the half-life should depend exponentially on the alpha particle energy. Nobody had a mechanism. Gamow's calculation provided the mechanism. The logarithm in the Geiger-Nuttall law comes from the exponential tunneling probability. Higher energy alpha particles face a narrower effective barrier because their energy is closer to the top of the Coulomb potential. Narrower barrier means higher tunneling probability. Higher tunneling probability means shorter half-life. The slope of the Geiger-Nuttall line is determined by the nuclear charge and the barrier shape. Everything falls into place. 17 years of empirical data explained in a single calculation. A pattern that had been sitting in the data, beautiful and unexplained, suddenly had a reason. And the reason was that the nucleus is not a fortress. It is a cage with permeable walls, and the permeability depends exponentially on how thick the walls are. I want to emphasize what this meant for physics in 1928. Before Gamow, before Gurney and Condon, quantum mechanics had been applied to atomic physics, to electrons orbiting nuclei, to the hydrogen spectrum, to the behavior of atoms in electric and magnetic fields. It had not been applied to the nucleus itself. Nobody knew if the new quantum theory worked inside the nucleus. Nobody knew if the same rules that governed electrons at the atomic scale applied to protons and neutrons at the nuclear scale. Gamow's paper was the first time quantum mechanics was successfully applied to a nuclear process. It demonstrated that the quantum revolution was not limited to the outer layers of the atom. It reached all the way in. The nucleus obeyed quantum mechanics. The stronghold of the atom followed the same rules as its periphery. And the implications of that fact, the fact that nuclear processes are quantum processes, would lead within 20 years to nuclear reactors, nuclear weapons, and the complete transformation of geopolitics, all from a wave function leaking through a wall. And Gurney and Condon saw the same thing. Their Nature paper, published September 22nd, 1928, opens by noting that radioactive decay had been known since 1902, that the exponential decay law was established, that the time of disintegration was independent of the atom's previous history and depended solely on chance. They wrote that previously it had been necessary to postulate some special instability of the nucleus to explain decay. But now, they said, disintegration is a natural consequence of the laws of quantum mechanics without any special hypothesis. Without any special hypothesis. That sentence deserves more attention than it gets. What Gurney and Condon were saying is that radioactive decay is not an anomaly that requires a special explanation. It is not something extra that nature does on top of quantum mechanics. It is quantum mechanics. The wave function leaks. The probability is non-zero. The particle escapes. That is all. The behavior that had mystified physics for a quarter century was just the Schrödinger equation doing what the Schrödinger equation does. The nucleus was not unstable in any special way. The wave function was simply being honest about probability, and probability does not respect walls. Their longer paper, published in Physical Review, Volume 33 in February 1929, contains the analogy that became the most successful pedagogical image in 20th century physics. They wrote that if a ball is moving in a valley and does not have enough energy to get over a mountain on one side, it must certainly stay in the valley for all time. But this is not so in quantum mechanics. The ball will have a small but finite chance of slipping through the mountain and escaping from the valley, slipping through the mountain, not climbing over it, not drilling through it, slipping, as if the mountain were not quite solid, as if reality had a porosity that classical physics refused to acknowledge. And then there was Hund, Friedrich Hund, born February 4th, 1896, in Karlsruhe, Germany, working in Copenhagen and Göttingen in 1926 and 1927. Hund was studying molecular spectra. He was trying to understand why certain energy levels in molecules were split in ways that existing theory could not explain. The answer, he realized, was tunneling, inner symmetric double well potential. Like the one created by two atoms bonded together, a particle can tunnel from one well to the other. The rate of tunneling determines the splitting of energy levels. Hund worked this out in a series of papers, the most important submitted from Göttingen in May 1927 and published in Zeitschrift für Physik, Volume 43, page 805. He even calculated the tunneling periods for barriers of different heights and showed that a tiny change in barrier height could shift the tunneling time from nanoseconds to a billion years. He understood the exponential. He saw how savage it was. He built a table showing the relationship between barrier height and tunneling period. And if you look at that table today, it reads like a prophecy. Small barrier, fast tunneling. Tall barrier, slow tunneling. Taller barrier, unimaginably slow tunneling. The numbers span 30 orders of magnitude in a column that covers half a page. He saw the whole story in 1927. The exponential that powers the sun. The exponential that keeps your body intact. The exponential that separates the false vacuum from the true vacuum. All of it implicit in Hund's table. But Hund's tunneling was molecular. It was bound state to bound state, one well to another. He did not apply it to a continuum problem. He did not use it to solve the paradox of alpha decay. He did not give it a dramatic physical application that would make newspaper headlines. And there is a deeper reason he did not get credit, one that has to do with how physics assigns importance. Alpha decay was a mystery. It had been a mystery since Rutherford. It involved the nucleus, the frontier of physics in 1928. It connected to radioactivity, which connected to energy, which connected to weapons, which connected to power. Molecular energy level splittings, by contrast, were a chemistry problem. Spectroscopy. Important, yes, but not glamorous. Not urgent, not the kind of thing that gets discussed over dinner at Solvay conferences. Hund solved tunneling in the kitchen, while Gamow and Gurney and Condon solved it in the ballroom. The kitchen work came first. The ballroom work got the credit. And there is something else. Hund did not coin the word tunneling. He did not give the phenomenon a name that would stick. In his papers, he described the barrier penetration mathematically, but did not frame it as a general principle, with a catchy label. Naming matters in physics more than physicists like to admit. Schrödinger's cat, Bell's theorem, the Heisenberg uncertainty principle. These names carry the ideas through history. Hund's tunneling had no name. It was just a calculation in a paper about molecular spectra, and calculations without names get forgotten. When Gamow and Gurney and Condon published their alpha decay papers a year later, it was their work that got the credit. Their names attached to tunneling, their careers defined by it. The simultaneous, independent discovery was dramatic enough to earn a place in physics folklore. The earlier, quieter discovery was not. Hund got Hund's rules, which every chemistry student memorizes, and a street in Göttingen named after him 7 years after he died. He lived to 101. He outlived Gamow by 29 years. He outlived Condon by 23 years. He outlived Gurney by 44 years. The man who saw tunneling first saw everything that came after, and almost nobody remembers that he saw it first. I want to say something about what it means to live that long, in the shadow of your own discovery. Hund watched the entire 20th century from inside physics. He watched the alpha decay papers become famous. He watched tunneling become a field. He watched the tunnel diode, the Josephson junction, the scanning tunneling microscope. He watched 4 Nobel Prizes get awarded for applications of the phenomenon he discovered first. He watched younger physicists learn tunneling from textbooks that did not mention his name. And he kept working. He kept teaching. He kept publishing. He moved from Rostock to Leipzig, to Jena, to Frankfurt, to Göttingen. He supervised students. He attended conferences. He lived quietly, productively, and in almost total obscurity relative to the magnitude of what he had done. There is a kind of courage in that, or a kind of resignation. I genuinely do not know which. Robert Mulliken, who won the 1966 Nobel Prize in Chemistry for molecular orbital theory, said privately that his prize should have been shared with Hund. It was not. There is a pattern here, and the pattern has nothing to do with the quality of the physics. But here is where the story turns. Because up to this point, what I have described is a triumph. 3 independent discoveries of the same truth. A puzzle solved. Physics advanced. A kind of story that should end with Nobel Prizes and professorships and quiet academic careers. And for one of the 3, it nearly did. For the other 2, the 20th century had something else planned. Something that connects directly to why you were never taught the full version of the story. Gamow went home. After his summer in Göttingen, after his triumph, he returned to the Soviet Union. And the Soviet Union in the late 1920s and early 1930s was becoming a place where the words "returned home" could function as a death sentence. By 1931, Gamow had been elected a corresponding member of the Soviet Academy of Sciences. He was 28 years old, one of the youngest members in the Academy's history. The state celebrated him. They used his work. They pointed to him as proof that Soviet science was the equal of Western science. And then they closed the door. Travel permits that had been routine began to be denied. International conferences that Gamow had attended freely became impossible to reach. The state that had celebrated his discovery now treated him as an asset to be contained. I want to be specific about what was happening in the Soviet Union during this period, because the vagueness of phrases like Stalinist repression has a way of draining the reality out of them. In the early 1930s, Stalin's regime was consolidating control over every institution in the country, including the sciences. Physicists were being required to demonstrate ideological alignment. The sciences were not exempt from the demand for orthodoxy. They were a specific target. Quantum mechanics itself was under suspicion in certain circles because it conflicted with dialectical materialism. The uncertainty principle, the idea that nature has fundamental limits on what can be known, was seen by some Soviet ideologues as bourgeois defeatism. The correct Marxist position, according to these ideologues, was that nature is fully knowable and that uncertainty is a product of capitalist science's failure to look hard enough. There were actual conferences, actual organized sessions, where physicists were expected to explain how their work aligned with Marxist-Leninist philosophy. The idea that a mathematical description of nature should answer to political philosophy would be laughable if it had not gotten people killed. And it did get people killed. Not metaphorically, not through career damage, through bullets and prison cells and firing squads. The Great Purge of 1937 and 1938 swept through every institution in the Soviet Union, including the physics institutes. The NKVD did not make fine distinctions between physicists who were politically engaged and physicists who just wanted to solve equations. If you were prominent, if you had international connections, if you had traveled abroad, if someone who disliked you wrote a letter to the authorities suggesting that your work was ideologically suspect, you could be arrested, interrogated, tortured, and executed within weeks. The paperwork was minimal. The trials, when they happened at all, were performances that lasted minutes. The sentences were predetermined. The appeals were non-existent. Fritz Houtermans, a German communist physicist who had fled to the Soviet Union to escape the Nazis, was arrested by the NKVD in December 1937 and tortured. His wife appealed to every authority she could reach. Nobody helped. The NKVD eventually handed Houtermans to the Gestapo as part of the Molotov-Ribbentrop Pact. He went from a Soviet prison to a German prison, from one set of torturers to another. He survived the war and eventually returned to physics. But the fact that the Soviet Union, a country that claimed to represent the progressive forces of history, traded a physicist to the Nazis like a commodity, tells you everything you need to know about how the state valued its scientists. They were assets, tools, and tools that become inconvenient can be discarded. Gamow wanted out, And here is the irony that should not be lost. The man who had proved that particles can escape through impenetrable barriers could not escape through a border. In the summer of 1932, Gamow and his wife, Lyubov Vokmintseva, who he called Ro, a physicist in her own right, attempted to flee the Soviet Union by kayak. I want you to sit with that sentence for a second. A theoretical physicist, a man whose tools were pencils and differential equations, decided to paddle a kayak across the Black Sea. The plan was to launch from the Crimean coast and paddle to Turkey. 250 kilometers of open water that gets rough without warning, in a region where the weather changes faster than you can turn a small boat around. They packed food, water, and, according to Gamow's own memoir, chocolate and coffee, which is the supply list of either a very optimistic physicist or a deeply desperate one. They launched, they paddled, and the Black Sea, which does not care about quantum mechanics or political persecution, or the thermodynamic implausibility of crossing it in a kayak, sent a storm. It drove them back. They made it partway across and were forced to turn around. They returned to the Crimean coast, exhausted and soaking, and alive. Nobody noticed. The border guards did not know. The NKVD did not know. The state did not know they had tried. Think about Gamow in that kayak. Think about the man who had mathematically described how a particle escapes through a barrier it does not have the energy to cross, sitting in a small boat on a large sea, trying to escape through a barrier he did not have the resources to cross. The irony is not poetic, it is literal. Tunneling works because the probability is non-zero and the number of attempts is large. Gamow's kayak crossing was a single attempt with a very low probability of success. The math was against him, and the math won. There was a second attempt, this time from Murmansk, in the far north, trying to reach Norway across the Arctic waters, also by kayak or small boat, also failed, also undetected. 2 attempts, 2 failures. The particle bounced back from the barrier, but unlike an alpha particle, Gamow did not have 10 billion years to keep trying. I need to pause here because I want to be honest about the sourcing. These escape attempts come almost entirely from Gamow's own posthumous memoir, My World Line, published in 1970. They are not corroborated by Soviet records. The specific details, the chocolate, the storm, the Murmansk attempt, are Gamow's recollection. They are consistent with what we know about his character and his circumstances, and no historian has seriously doubted them. But I want you to know that we are relying on one man's word. That said, what is not in doubt is the desperation. What is not in doubt is that Gamow was trapped, and what is not in doubt is what was happening to his colleagues who did not get out. Matvei Bronstein, one of the 3 musketeers of Leningrad, the young theorist who worked on quantum gravity before anyone else took the subject seriously, was arrested by the NKVD in August 1937. He was charged with being a member of a counter-revolutionary terrorist organization. He was tried in a session that lasted about 20 minutes. He was sentenced to death. He was shot in February 1938. He was 31 years old. Lev Shubnikov, a brilliant experimental physicist who ran the cryogenics laboratory at the Ukrainian Physico-Technical Institute in Kharkov, was arrested in the same wave of purges. He was shot on November 10th, 1937. He was 36. Lev Landau, Gamow's fellow musketeer, was arrested in April 1938. He was accused of being a German spy. He was interrogated. His ribs were broken. He spent a year in prison. He was freed only because Pyotr Kapitsa, who had enough political capital to take the risk, personally wrote to Molotov and argued that Landau was needed to explain the phenomenon of superfluidity. Kapitsa essentially told the Soviet government that they could not understand their own physics without the man they were torturing. And it worked. Landau was released. He went on to win a Nobel Prize, but he was never the same. Had Gamow stayed in the Soviet Union, he almost certainly would not have survived 1937 and 1938. He knew this. He tried the kayak twice. When that failed, he waited. And then, in October 1933, an opportunity arrived in the form of a physics conference. The 7th Solvay conference was held in Brussels from October 22nd to October 29th, 1933. The theme was the structure and properties of atomic nuclei. It was the most important gathering of physicists in the world. Gamow needed to attend, but the Soviet government would not give him a travel permit, not for one person. The state did not let valuable assets travel alone to capitalist countries. Gamow negotiated. He argued that he needed to bring his wife. The request went up the chain. Eventually, it reached Bukharin and Molotov, who reluctantly granted both passports. This was extraordinarily unusual. Soviet physicists were sometimes allowed to attend foreign conferences. They were almost never allowed to bring their families. The fact that both passports were approved suggests either that someone high up trusted Gamow's loyalty or that someone was very bad at reading people. Gamow went to Brussels, and at the Solvay conference in October 1933, he looked around the room and decided he was never going back. The photograph from that conference is one of the most famous images in physics. In the front row sit Schrödinger, Irene Joliot-Curie, Niels Bohr, Marie Curie, Paul Langevin, Rutherford. Behind them stand Heisenberg, Fermi, Dirac, Pauli, Chadwick. And at the back, taller than everyone else in the frame, stands George Gamow, the man who would not go home. If you look at that photograph long enough, it starts to feel like a countdown. Within 8 months, Marie Curie would be dead. Within 6 months after that, Irene and Friedrich Joliot-Curie would announce artificial radioactivity and win a Nobel Prize. Within 5 years, Lise Meitner, who is not in this photograph but should have been, would flee Nazi Germany and co-discover nuclear fission. Within 12 years, several of the men in this photograph would be building an atomic bomb. And Gamow, standing at the back, a head taller than everyone, would be in Washington, D.C., safely on the other side of the barrier, working on problems that ranged from nuclear physics to cosmology to genetics, never going back to the country that had made him, never seeing the friends who had not gotten out. But there was a complication. Niels Bohr had personally arranged for Gamow's invitation. He had given Paul Langevin a guarantee that Gamow would return to the Soviet Union. Bohr had staked his personal reputation on it. When Gamow told Bohr that he intended to defect, Bohr faced a crisis of conscience. He had made a promise, but the promise required returning a man to a country that was killing physicists. Marie Curie intervened. She went to Langevin and persuaded him to release Bohr from his guarantee. Curie understood what was at stake. She was 66 years old. She had less than a year to live. She would die on July 4th, 1934, of aplastic anemia caused by decades of radiation exposure. But in October 1933, this woman who had personally handled radioactive materials that were undergoing the very alpha decay that Gamow had explained, the woman whose hands were scarred by the radiation produced by tunneling particles, used the last months of her authority to save the man who had explained why those particles escaped. She offered Gamow a temporary position at the Curie Institute in Paris, to give him a legal foothold in the West. I am telling you this not because it is interesting background. I am telling you because the connections in this story run so deep that they almost feel engineered. Marie Curie isolated radium. Radium undergoes alpha decay. Alpha decay is quantum tunneling. Gamow explained quantum tunneling. And Marie Curie, dying of the radiation produced by the phenomenon Gamow explained, saved Gamow's life. The physics and the people are not separate threads. They are the same thread running through every decade of the 20th century. Within months, Gamow had moved through Paris, Copenhagen, and Cambridge. He spent time at the Cavendish laboratory with Rutherford, the same Rutherford who had identified the paradox that Gamow solved. By the autumn of 1934, he was a professor at George Washington University in Washington, D.C. He would stay there until 1956, before moving to the University of Colorado at Boulder. He never returned to the Soviet Union. He never saw Leningrad again. Gamow escaped. The particle slipped through the barrier. But tunneling does not care about your intentions. It does not care whether what escapes is a helium nucleus, or a physicist, or a bubble of something far more dangerous. It just happens. The wave function leaks. The probability is non-zero. And once the transition begins, nothing on either side of the barrier can stop it. You might think that is the end of the hard part. Gamow is in America. His co-discoverers, Gurney and Condon, are already in America. The physics is published. The careers should proceed. The story should quiet down. But what America did to Gurney and Condon, the country that was supposed to be the safe side of the barrier, was in its own way just as destructive as what the Soviet Union tried to do to Gamow. Just quieter, just slower. And with paperwork instead of bullets, the destruction of Edward Condon began on March 1st, 1948. By that year, Condon was one of the most decorated physicists in the United States. He was the director of the National Bureau of Standards. He was a past president of the American Physical Society. He had contributed to the Manhattan Project. He had helped build the scientific infrastructure that won the war. And on March 1st, 1948, a man named J. Parnell Thomas, a Republican congressman from New Jersey who chaired the House Un-American Activities Committee, issued a report from his hospital bed. Thomas was recovering from gastrointestinal hemorrhages. He was in no condition to be chairing anything. But from that hospital bed, he called Edward Condon one of the weakest links in our atomic security. I want to make sure you understand what just happened. A congressman who was recuperating from internal bleeding publicly declared that one of America's most accomplished physicists was a security threat, not based on evidence of espionage, not based on evidence of disloyalty, based on the fact that Condon had attended a meeting with a Polish diplomat and had advocated for open scientific exchange. Thomas also called Condon Dr. Condom and the missing link. These were the insults of a man who did not understand the science and did not care to. This was not an investigation. It was a performance. Here is where I need to correct something you were probably taught, or at least something you absorbed from the cultural shorthand around McCarthyism. You were taught that McCarthy and HUAC targeted Hollywood actors and State Department officials. That is true, but what is almost never discussed is that they also targeted the physicists, not the weapons designers, the theorists, the people who understood the fundamental physics underneath the bomb. Condon, David Bohm, who was indicted by HUAC in December 1949, suspended by Princeton, acquitted, and then forced into exile anyway, first to Brazil, then to Israel, then to London, where he spent the rest of his career. Robert Oppenheimer, whose security clearance was stripped in 1954 in a hearing that contained no evidence of disloyalty. The country that built the atomic bomb spent the next decade systematically hounding the people who had built the physics underneath it. Condon fought back. At a hearing before a loyalty board, when asked whether he had been at the forefront of a revolutionary movement in physics called quantum mechanics, Condon responded with a statement that I wish every physics student were required to memorize. He said, "I believe in Archimedes' principle, formulated in the 3rd century BC. I believe in Kepler's laws of planetary motion, discovered in the 17th century. I believe in Newton's laws." And he continued, through the Bernoullis, through Fourier, through Ampere, through Boltzmann, through Maxwell. He was making a point. Quantum mechanics is not a revolution. It is the next step in a continuum of understanding that stretches back thousands of years. And the idea that believing in it is a form of political subversion is so stupid that it would be funny if it had not cost real people their careers and their health, and, in at least one case, their life. I want to stay with Condon for a moment longer, because the texture of what happened to him gets lost in the summary. The persecution was not a single event. It was a slow grinding, years of hearings, years of forms, years of having to explain over and over to people who did not understand what a wave function was, that attending a scientific conference is not espionage and that talking to a Polish diplomat is not treason. Condon's colleagues watched this happening. Some spoke up. The American Physical Society passed a resolution defending him. The scientific community largely rallied, but the political machinery did not care about resolutions. It cared about headlines, and the headline, "Top Physicist Cleared of Disloyalty," does not sell newspapers the way Weakest Link in Atomic Security does. The accusation always travels farther than the acquittal. Condon knew this. He watched it happen in slow motion. There is a detail from this period that I have not been able to stop thinking about. After Condon left the Bureau of Standards, after the clearance was revoked for the final time, after Nixon took his victory lap in Montana, a friend of Condon's noted that he was never quite the same cheerful man afterward. That phrase, "never quite the same cheerful man," that is what institutional persecution does. It does not always kill you. Sometimes it just dims the light. Slowly, over years, until the person you were before the first hearing is someone you cannot quite get back to. President Truman publicly defended Condon. At the American Association for the Advancement of Science meeting in September 1948, Truman called HUAC the most un-American thing we have to contend with today. The Atomic Energy Commission cleared Condon in July 1948. His security clearance was restored, and then revoked again, and then restored, and then, on October 21st, 1954, Secretary of the Navy Charles S. Thomas suspended Condon's clearance once more, and Vice President Richard Nixon, campaigning in Montana at the time, publicly took credit for it. Think about that. The Vice President of the United States publicly boasted about destroying the security clearance of one of the country's leading physicists, not because Condon had done anything wrong, not because there was evidence, because it played well in Montana, because in 1954, in the United States of America, ruining a physicist was good politics. Condon resigned from the Bureau of Standards, effective September 30th, 1951. He moved to Corning Glass Works in the private sector, where he could work without a government security clearance and without the constant threat of investigation. He was re-cleared in July 1954 because the industrial work at Corning required it, and then had the clearance suspended again 3 months later by the Navy. The cycle was endless. Clearance, accusation, investigation, clearance, accusation, investigation. Each round a little more exhausting, each round taking another piece of the cheerful man. He eventually gave up. He stopped fighting. He taught at Oberlin College. He taught at Washington University in St. Louis. He ended up at the University of Colorado and the Joint Institute for Laboratory Astrophysics. In the mid-1960s, the Air Force asked him to direct a study on unidentified flying objects. The Condon Committee, as it came to be known, operated from 1966 to 1968 and produced what is known as the Condon Report. The man who proved particles walk through walls spent the twilight of his career investigating flying saucers. Not because he believed in them, because the same government that had destroyed his physics career needed someone credible to make the UFO problem go away. That was the only use they still had for Edward Condon. They did not trust him with nuclear secrets. They trusted him with alien spaceships. The distinction tells you everything you need to know about what McCarthyism valued and what it did not. And Condon was not alone. I want to zoom out for a moment because the individual tragedies taken one at a time can look like bad luck. Taken together, they look like a policy. David Bohm had been at Princeton. He was one of the most original thinkers in quantum mechanics. In 1951, he published a textbook on quantum theory that was so good that Einstein invited him for conversations about the foundations of the subject. In the same year, he produced a hidden variable interpretation of quantum mechanics that challenged the Copenhagen orthodoxy, and that, decades later, would be vindicated by Bell's theorem experiments. But Bohm had been a member of the Communist Party in the late 1930s, when he was a graduate student at Berkeley. He had left the party long before his work at Princeton. It did not matter. HUAC subpoenaed him in December 1949. He refused to testify about colleagues. He was indicted for contempt of Congress. Princeton suspended him. He was acquitted in June 1951, but Princeton did not reinstate him. No American university would hire him. He left the country. He went to the University of Sao Paulo in Brazil. The State Department confiscated his passport. He was trapped in Brazil the same way Gamow had been trapped in the Soviet Union, a physicist exiled by his own country for the crime of having attended meetings in graduate school. He eventually moved to the Technion in Israel, then to Birkbeck College in London, where he spent the rest of his career and died in 1992. He never returned to American academia. Robert Oppenheimer, the father of the atomic bomb, the man who ran Los Alamos, whose security clearance was revoked in June 1954 after a hearing that lasted 4 weeks, involved 40 witnesses, and produced no evidence of disloyalty. The hearing was driven by Lewis Strauss, chairman of the Atomic Energy Commission, who had a personal vendetta against Oppenheimer. The vote to revoke was 2-1. Oppenheimer spent the rest of his life at the Institute for Advanced Study in Princeton, stripped of his clearance, stripped of his advisory roles, unable to contribute to the defense establishment he had helped create. He died of throat cancer in 1967. Bohm, Condon, Oppenheimer, Gurney. 4 physicists, 4 destroyed careers. Not one of them was a spy. Not one of them was convicted of anything related to national security. They were destroyed by association, by suspicion, by the weaponization of paranoia against the people who had built the very science the country claimed to be defending. And the physics community, with a few notable exceptions, watched it happen. Truman defended Condon. Einstein defended Bohm. Kapitsa defended Landau. But most physicists kept their heads down and hoped the storm would pass. the League of the Fearful. He died of heart disease in Boulder, Colorado, on March 26, 1974, the same city where Gamow had died 6 years earlier. And then there was Gurney. And what happened to Gurney is in some ways worse than what happened to Condon, because at least Condon's persecution was public. At least people knew his name. At least there were headlines and speeches, and a president defending him on a stage. Gurney's destruction was quiet, almost invisible, almost unnoticed. After the tunneling paper, Gurney had built a serious career. He wrote Elementary Quantum Mechanics in 1934. He wrote Ions in Solution in 1936. With Neville Mott, he wrote Electronic Processes in Ionic Crystals in 1940, a book so important that it gave physics the Mott-Gurney law for space charge limited current. This is not a man who published one paper and coasted. This is a man who was building a body of work. But Gurney had two problems. His wife, Natalie Kaltenikoff, was Russian-born, and in the 1930s, when they were both in Bristol, they had known a young German refugee physicist named Klaus Fuchs. Fuchs was a PhD student under Neville Mott. He was quiet. He was private. He and the Gurneys were members of the Bristol branch of the Society for Cultural Relations with the USSR. Mott later recalled a 1936 meeting of the society where Fuchs participated in a mock trial recreation and took the role of the prosecutor, Wyszynski. Mott remembered that Fuchs threw away his shyness and attacked the accused with a venom that showed clearly where his sympathies lay. But at the time, nobody thought much of it. Fuchs was a refugee from Nazi Germany. Having leftist sympathies was not unusual or suspicious. It was, for a German fleeing fascism, arguably rational. In January 1950, Klaus Fuchs confessed to having passed atomic secrets to the Soviet Union. He had been a spy the entire time, from his work at Los Alamos, through his post-war position at the Harwell Atomic Research Center in Britain. Fuchs had been feeding nuclear weapons information to Moscow. The confession detonated across the Western intelligence community, and the blast radius reached Ronald Gurney. The FBI worked backward through every connection Fuchs had ever had, and they found Gurney. They found the Bristol connection. They found the Society for Cultural Relations membership. They found that Natalie was Russian-born, and they found that Gurney had visited Fuchs at Harwell in September 1949, just months before the confession. The visit was innocent. Gurney was looking for a position in the UK. He had written to John Cockcroft, who ran the Harwell laboratory, inquiring about opportunities. Cockcroft was away when Gurney arrived. Fuchs, as a senior member of the Theoretical Physics Division, was deputized to show Gurney around. They had tea. They discussed physics. They talked about the laboratory's research programs. It was a professional visit, a physicist visiting a research facility, hosted by another physicist. In any other context, in any other decade, it would have been completely unremarkable. But this was not any other decade. This was the decade when a man's career could be destroyed by a cup of tea with the wrong person. And Klaus Fuchs was the worst possible person. American security did not believe in coincidences. Not anymore. Not after the worst atomic espionage case in history. The fact that Gurney had visited Fuchs at Harwell, even briefly, even innocently, was entered into the file as an unexplained and unnecessary visit. The phrasing is from the security reports. Unexplained, unnecessary. As if a physicist visiting a laboratory needed to justify his presence. As if scientific curiosity were a suspicious motive. Gurney was denied security clearance at Brookhaven National Laboratory in 1947. He was denied at the Applied Physics Lab in 1949. In January 1950, the National Bureau of Standards denied his clearance. The denial letter, which has been quoted in a recent paper, Reconstructing Gurney's Life by Brian Pollard and Saman Alavi, published on Arxiv in June 2025, stated that Natalie Gurney had been consistently associated with organizations which are communistic or follow the Communist Party line, and that the association was detrimental to the best interests of the United States government. Aberdeen Proving Ground denied him too. Every door closed, one by one, like barriers going up around a nucleus, except in reverse. The barriers were not keeping something dangerous inside. They were keeping a physicist out. During the FBI investigation, agents interviewed Fuchs himself about Gurney. Fuchs, the actual spy, the man who had betrayed every nuclear secret he ever touched, who had been passing weapons designs to the Soviet Union for years while smiling at his British colleagues over lunch, told the FBI that he considered Gurney a security risk and called Natalie not sufficiently discreet. Think about the absurdity of that. The most dangerous spy in the history of the Western nuclear program was being asked to evaluate the trustworthiness of a physicist whose only crime was knowing him socially in the 1930s. And the FBI took his assessment seriously. They wrote it down, they put it in the file, they used it. The Gurney's house in College Park, Maryland, was placed under FBI surveillance from January to April 1951. Agents watched who came and went. They logged the visitors. They wrote reports. They watched a physicist and his wife live their daily lives, go to the grocery store, receive mail, host dinner guests. All of it documented, all of it catalogued, all of it scrutinized for evidence of a conspiracy that did not exist. Then, in April 1952, the University of Maryland President Harry Clifton Curly Bird expelled Gurney and 5 other professors from the university. There were no hearings, no formal charges, no due process, no appeal. Just gone. Bird was a political operator who understood which way the wind was blowing, and the wind in 1952 was blowing toward anyone with a Russian-born spouse and a connection, however remote, however innocent, however meaningless, to Klaus Fuchs. Bird made a calculation. The calculation was that firing 6 professors was cheaper than defending them. And he was right. Nobody defended them. The League of the Fearful looked the other way. Gurney could not find permanent academic employment after that. The man who co-authored one of the foundational papers of nuclear physics, who wrote canonical textbooks, who gave the world the Mott-Gurney law, could not get a job. Because his wife was Russian. Because he had once had coffee with Klaus Fuchs in Bristol in 1936. Because the United States of America in 1952 had decided that the social connections of a physicist's spouse were more important than the physicist's contributions to human knowledge. He took a visiting research position at Maryland's Institute for Fluid Dynamics, which apparently did not report to the same administration that had expelled him. He was working there, trying to rebuild, trying to do physics again, when his body gave out. On April 14th, 1953, Ronald Wilfred Gurney suffered a cerebral hemorrhage in his New York City apartment. He had experienced a retinal hemorrhage a few days earlier, a warning sign that something was wrong with his blood vessels. A doctor arrived within half an hour. It was too late. Gurney was dead. He was 54 years old. There was no memorial service. Nobody organized one. Nobody stood up and said, "This man helped explain how the universe works. This man co-wrote the most beautiful sentence in nuclear physics." This man was destroyed not by his own failures, but by the cowardice of the institutions that should have protected him. Nobody said any of that. The League of the Fearful stayed silent. Natalie Gurney called them casualties of the Cold War. She called the colleagues who stayed silent the League of the Fearful. When Gurney's final academic work, a chapter on ionic crystals, was published posthumously in Condon's Handbook of Physics in 1958, his institutional affiliation was listed as the University of Bristol, not any American university. 5 years after his death, Natalie believed that there was still fear of being associated with Ronald in American academia. 5 years after his death, and his name was still radioactive. Not in the physics sense, in the political sense. The kind of radioactivity that the Geiger counter of institutional cowardice picks up from across a room. The man who wrote that the alpha particle slips away almost unnoticed had himself slipped away from physics, almost unnoticed. He left behind a wife, a body of work that is still cited today, and a story that almost nobody knows. I have been reading physics history for a long time, and until I started researching this script, I have never heard of Ronald Gurney. That fact alone should tell you something about what the 20th century did to the people who discovered tunneling. And now I need to talk about J. Parnell Thomas, because the coda to this story is so grotesque that if I did not have the documented record, I would not believe it myself. Thomas, the congressman who called Condon the weakest link in America's atomic security. Thomas, who launched the persecution from a hospital bed. Thomas, who called a physicist Dr. Condon in official proceedings. Thomas, whose grasp of science was so tenuous that he once asked Condon if he had been at the forefront of a revolutionary movement in physics called quantum mechanics, as if quantum mechanics were a political party, rather than a description of reality. In 1948, the same year he went after Condon, the same year he was attacking the loyalty of scientists whose work he could not understand. J. Parnell Thomas was indicted for a salary kickback scheme. He had been padding his congressional payroll with fake employees. 2 of them were named Myra Midkiff and Arnett Miner. These were not real people doing real work. They were names on a payroll, their salaries flowing directly into Thomas's pocket. The man who accused Edward Condon of being a threat to national security was stealing taxpayer money using imaginary employees. The man who questioned the loyalty of physicists who had served their country with distinction was a common thief. He was convicted. He was sentenced to 6 to 18 months in federal prison and a $10,000 fine. He did not testify in his own defense. He pleaded no contest, and here is the part that makes this story feel less like history and more like dark comedy written by someone with a very specific sense of irony. Thomas served his time at the Danbury Federal Correctional Institution in Connecticut. And at Danbury, Thomas found himself incarcerated alongside Ring Lardner Jr. and Lester Cole, 2 members of the Hollywood 10, screenwriters who Thomas himself had helped send to prison for contempt of Congress for refusing to name names. The man who sent people to prison for their political beliefs ended up in the same prison as his own victims. They ate in the same dining hall. They walked the same corridors. They shared the same walls. Thomas was pardoned by Truman on Christmas Eve 1952. He returned to private life. He died in 1970. There is no evidence that he ever reflected on the irony. There is no evidence that he ever thought about Edward Condon or Ronald Gurney, or what his performance of patriotism cost the men who had actually contributed to the country's security. He lived to 75. He outlived Gurney by 17 years. He got out of prison and went home and lived a quiet life, while the physicist he persecuted died of a cerebral hemorrhage in a New York apartment with no memorial service. That is the 20th century in miniature. The fraud went home. The physicist died alone. You would think that the physics, at least, would be untouched by all of this, that the equations do not care who is persecuted, that the wave function leaks through its barriers regardless of what happens to the people who wrote the equations down. And that is true. The physics kept working. It kept revealing things. But I want to point something out before we go further into the physics, because I think it matters. The persecution of Condon and Gurney and Bohm and Oppenheimer did not just destroy individual careers. It changed what American physics was willing to think about. For decades after the McCarthy period, American physicists avoided foundational questions. They avoided the interpretation of quantum mechanics. They avoided asking what the wave function actually means, what measurement actually does, whether hidden variables are possible. These questions were associated with people who had been purged. Bohm was the most prominent example. His hidden variable interpretation, published in 1952, was dismissed not because it was wrong, but because it was associated with a man who had been politically tainted. The physics of foundations was contaminated by the politics of loyalty, and the result was decades of lost progress. John Bell, working at CERN in the 1960s, essentially had to rediscover the question that Bohm had asked, because the American physics community had buried it along with Bohm's career. The destruction of Condon and Gurney and Bohm was not just a human tragedy, it was an intellectual crime. It cost physics decades of progress on its most fundamental questions, and the cost was invisible because you cannot measure the papers that were never written, the questions that were never asked, the students who were never inspired by the scientists, who were never given the chance to teach. But the tunneling itself, the raw physics, that kept working, and what it revealed in the decades after Gamow and Gurney and Condon is that tunneling is not a small phenomenon confined to radioactive nuclei. It is not a niche result. It is the silent engine that drives nearly everything in the physical universe. And the scale of what it does, once you actually follow the implications, is the part of this story that should unsettle you more than the politics. Because the politics destroyed careers. But the physics threatens everything. I want to start with the sun, because every time you feel sunlight on your skin, every time you look up at a clear sky and register the warmth of the nearest star, you are experiencing a direct consequence of quantum tunneling. And the numbers involved are so extreme that I need to walk through them carefully, because the extremity is the point. The sun's core sits at a temperature of about 15.7 million Kelvin. That sounds hot. It is hot. It is hot enough to fully ionize every atom, to strip every electron from every nucleus, to create a plasma of bare protons and electrons at densities of about 150 grams per cubic centimeter, roughly 10 times the density of lead. But here is the problem. It is not hot enough. For two protons to fuse, they need to get close enough for the strong nuclear force to grab them. The strong force has a range of about 1 femtometer, 10 to the negative 15 meters. At that distance, the attractive nuclear force overwhelms everything else, and the protons stick together. But to reach that distance, the two protons have to overcome their mutual electromagnetic repulsion. They are both positively charged. They repel each other. The energy required to push two protons close enough to touch is about 1 million electron volts, 1 MeV. That is the height of the Coulomb barrier. At 15.7 million Kelvin, the average thermal energy of a proton in the sun's core is about 1.4 thousand electron volts, 1.4 keV. The barrier is 1 MeV. The average proton has roughly 1,000th of the energy needed to overcome the barrier classically. If you use classical physics to calculate the probability of two protons with that thermal energy reaching contact distance, you get a Boltzmann factor of e to the negative 6, 170. That number, that right there, I need you to understand what that number is. e to the negative 670 is approximately 10 to the power of negative 290. That is not a small probability. That is not an unlikely event. That is a number so close to zero that it has no analogy in human experience. If every proton in the observable universe attempted a classical fusion event every Planck time for the entire age of the universe, the probability of even a single success would still be effectively zero. I want to be specific about why this should disturb you. This was known. By the late 1920s, after Eddington had established that the sun is powered by nuclear reactions, after the mass-energy equivalence of E equals mc squared was understood, physicists could calculate the Coulomb barrier height and compare it to the thermal energy of the solar core. They could see that the numbers did not work. The sun should not shine. The barrier is too high. The temperature is too low. And yet, there it is, in the sky, every morning, shining. Before Gamow, before tunneling, this was an unsolved crisis. Stars existed, and physics said they should not. The answer was sitting in a paper by a 24-year-old in Göttingen. A paper about radioactive decay. A paper about alpha particles escaping from nuclei. The same mechanism that lets particles out of a nucleus lets particles into a nucleus. Tunneling does not care about direction. It cares about probability. And the probability, while small, is not zero. Classically, the sun cannot shine. Classically, no star can shine. Classically, every star in the universe is a cold ball of hydrogen that will sit there forever doing nothing. The night sky should be dark. Your planet should be frozen. You should not exist. The temperature required for classical proton fusion would be roughly 3 billion Kelvin, about 200 times hotter than the sun's actual core. At that temperature, the protons would have enough thermal energy to simply climb over the Coulomb barrier without tunneling. But no main sequence star reaches 3 billion Kelvin. Not even close. The sun manages 15.7 million. The gap between what physics classically requires and what physics actually provides is a factor of 200. And the only thing that bridges that gap is the quantum mechanical leak of probability through a barrier that classical physics says is absolute. But the protons tunnel. Their wave functions leak through the Coulomb barrier. The tunneling probability, when you actually solve the Schrödinger equation for two protons approaching each other at solar core temperatures, is not zero. It is small, fantastically small, but it is not e to the negative 670. It is more like e to the negative 9 or e to the negative 10, depending on the exact energy. That is a difference of over 280 orders of magnitude. Tunneling does not just improve the odds slightly, it transforms an impossible event into a rare but viable one. And the sun compensates for the remaining smallness with sheer numbers. There are roughly 10 to the 57 protons in the sun's core. Each one is undergoing roughly 10 to the 14 collisions per second. At any given moment, the number of proton pairs attempting to fuse is so astronomically large that even a tiny tunneling probability, multiplied across all of those attempts, produces a steady rate of fusion. The rate is actually quite slow per proton. Any individual proton in the sun's core will wait, on average, about 10 billion years before it successfully fuses with another proton. The sun manages to shine not because fusion is easy, but because there are so many protons trying simultaneously that the aggregate rate is enough to power a star. I want to make that concrete. 10 billion years. That is the average wait time for a single proton. The sun is about 4.5 billion years old. Most of the protons in the sun right now have not yet fused. They are still waiting. they are still bouncing off the Coulomb barrier, being turned away, trying again. Billions of collisions per second, each one a failure, each one a rejection. And every now and then, roughly once every 10 billion years per proton, the wave function leaks through. The proton appears on the other side of the barrier. The strong force grabs it, and a tiny amount of mass is converted into energy. That energy works its way outward through the sun's interior over the course of about 170,000 years. 170,000 years. The photon that is hitting your retina right now as you look at the sun, if you were foolish enough to do that, started its journey from the core while Homo sapiens was still figuring out how to chip stone tools. It was bouncing around inside the sun, being absorbed and re-emitted, random walking its way outward from the core to the surface for the entire span of human cognitive evolution. And then it crossed the 8 light minutes of vacuum between the sun and the earth in about 499 seconds and landed on your face. Every photon of sunlight that has ever touched you began with a tunneling event. Every photon. I want to push this further, because the connection between tunneling and your existence is not just about the sun. It is about every atom in your body that is heavier than hydrogen. The carbon in your cells, the nitrogen in your DNA, the oxygen you are breathing right now, the iron in the hemoglobin that is carrying oxygen through your bloodstream as you listen to this. None of these elements existed after the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium. That is it. Everything heavier was forged inside stars, and every stage of stellar nucleosynthesis, every fusion reaction that builds carbon from helium, oxygen from carbon, silicon from oxygen, iron from silicon, depends on tunneling. The triple alpha process that builds carbon-12 from 3 helium-4 nuclei requires 2 successive tunneling events. The first creates an unstable beryllium-8 nucleus that lives for less than 10 to the negative 16 seconds. Before it decays, a third helium nucleus must tunnel in and fuse with it to create carbon-12. The probability of this happening is vanishingly small for any individual set of 3 helium nuclei. But there are enough helium nuclei in the core of a red giant star, and they are colliding frequently enough that the aggregate rate produces all the carbon in the universe. Fred Hoyle, the astrophysicist who first worked out the triple alpha process in the 1950s, realized that it would only work if carbon-12 has a nuclear resonance at a very specific energy, about 7.65 MeV above the ground state of carbon-12. This was a prediction, not a measurement, not a calculation based on existing data, a prediction based on the fact that carbon exists and therefore the resonance must exist. It was one of the most remarkable uses of the anthropic principle in the history of physics. Hoyle looked at the universe, noticed it contained carbon, and worked backward to determine what nuclear physics must be true for that to be possible. The resonance was found experimentally by William Fowler at Caltech in 1953, exactly where Hoyle said it would be. Fowler measured it. Hoyle predicted it. Fowler got the 1983 Nobel Prize in Physics for his work on nuclear reactions in stars. Hoyle did not. The committee gave the prize to the man who measured the resonance and excluded the man who predicted it. The pattern again. The pattern that runs through this entire story like a crack in a wall. The person who sees it first, who makes the intellectual leap, who says this must be true because the universe exists, does not get the prize. The person who confirms it with an apparatus does. Hund saw tunneling first and got nothing. Gamow predicted the cosmic microwave background and got nothing. Hoyle predicted the carbon resonance and got nothing. The Nobel Committee has a consistent preference for the hands that hold the instruments over the minds that tell the hands where to point. But the point is this: every atom of carbon in your body exists because of a chain of tunneling events inside a star that exploded before the sun was born. The supernova that scattered those atoms into the interstellar medium, the same medium that eventually condensed into the solar nebula that became the sun and the planets, was itself powered by fusion reactions that depend on tunneling. You are not just warmed by tunneling, you are made of it. Your body is a fossil record of tunneling events that happened in stellar cores billions of years ago. And tunneling reaches further still, into places you would not expect. In 1974, Stephen Hawking showed that black holes radiate. They emit particles. They have a temperature. This was shocking because black holes, by definition, are objects from which nothing can escape. The escape velocity is the speed of light. Nothing with mass and nothing without mass can cross the event horizon from inside to outside. And yet Hawking showed that black holes glow. They emit thermal radiation at a temperature inversely proportional to their mass. A stellar mass black hole has a temperature of about 60 billionths of a Kelvin, which is undetectable with any technology we have or can foresee. But the radiation is real, the physics is sound, and the mechanism at its core is tunneling. The standard popular explanation involves virtual particle-antiparticle pairs appearing near the event horizon, one falling in and the other escaping. This is a useful metaphor, but it is not really what happens. The actual calculation which Hawking performed using quantum field theory in curved space-time, is more subtle. The vacuum fluctuations of quantum fields near the event horizon create a situation where the outgoing mode of a field, the mode that would carry radiation away from the black hole, has a non-zero amplitude. There is a tunneling of field modes through the gravitational barrier of the event horizon. The black hole radiates because the wave function leaks through the barrier of space-time curvature at the horizon. Tunneling, again. In the most extreme gravitational environment in the universe, the same mechanism that lets alpha particles escape from uranium nuclei is letting radiation escape from black holes. Over unimaginably long timescales, around 10 to the 67 years for a solar mass black hole, Hawking radiation causes the black hole to lose mass and eventually evaporate completely. The most permanent objects in the universe, the objects that were supposed to swallow everything and give nothing back, turn out to be temporary, tunneling again. The wave function leaks. The probability is non-zero. Even the event horizon of a black hole is not truly impenetrable. Every photon of sunlight that has ever touched you began with a tunneling event. Every photon, not metaphorically, not poetically, literally. The first step of the proton-proton chain, the dominant fusion pathway in stars like the sun, requires two protons to tunnel through the Coulomb barrier and come close enough for one of them to undergo a weak interaction, converting a proton into a neutron and emitting a positron and a neutrino. Without tunneling, that first step does not happen. Without that first step, no deuterium is formed. Without deuterium, no helium-3. Without helium-3, no helium-4. Without any of that, no energy, no light, no heat, no photosynthesis, no food chains, no you, and it goes deeper than that. Tunneling does not just power the sun. It powers every star in the observable universe. Every star that has ever existed. Every star that ever will exist until the last red dwarf burns out trillions of years from now. The light from the most distant galaxy you have ever seen in a Hubble photograph started as a tunneling event. The heavy elements in your body, the carbon in your DNA, the iron in your blood, the calcium in your bones, were forged in the cores of stars that died before the sun was born. And every one of those stars was powered by tunneling. The carbon atom in the 6th position of a cytosine base in your DNA was manufactured inside a star that was burning because protons were tunneling through a barrier they did not have the energy to cross. You are, at the atomic level, a product of quantum tunneling, not philosophically, chemically. And there is another connection between tunneling and your DNA that is more direct and more unsettling. Proton tunneling in hydrogen bonds has been proposed as a mechanism for spontaneous point mutations. The hydrogen bonds that hold the base pairs of DNA together, the AT and GC pairs that encode your genetic information, are maintained by protons sitting in potential wells. These protons are not fixed in place. They are quantum mechanical objects. They have wave functions, and those wave functions extend beyond the walls of their potential wells. In 1963, a Swedish physicist named Per-Olof Lodin proposed that these protons could tunnel from one well to another, shifting from the normal tautomeric form to a rare form, creating a mismatch that the DNA replication machinery reads incorrectly. If the proton tunnels before replication, the wrong base gets inserted. A mutation occurs, not from radiation, not from a chemical mutagen, not from a copying error by an enzyme, from a proton walking through a wall inside your own DNA. The same mechanism that lets alpha particles escape from uranium nuclei, the same mechanism that makes the sun shine, operating inside the double helix of your genetic code. Lodin published his proposal in a volume called Advances in Quantum Chemistry in 1963. It was speculative at the time. The tools to test it experimentally did not exist. But in the decades since, computational quantum chemistry has advanced to the point where the tunneling rates can be calculated with reasonable precision. Several groups have confirmed that the barriers are thin enough and the tunneling probabilities are high enough to produce biologically relevant rates of tautomeric shift. A 2017 paper by Godbeer, Al-Khalili, and Sherwood in Physical Chemistry Chemical Physics used quantum mechanics and molecular dynamics simulations to show that proton tunneling in DNA base pairs occurs on timescales consistent with the observed rate of spontaneous point mutations. This is still an active area of research. The extent to which proton tunneling contributes to the overall mutation rate versus other mechanisms like oxidative damage and replication errors is debated. The numbers are not settled, but the mechanism is physically sound. The barriers are thin enough. The tunneling probabilities are non-zero. And if even a fraction of spontaneous mutations are caused by proton tunneling, then the engine of evolution, the raw material of natural selection, the source of every genetic variation that has ever mattered, every adaptation, every speciation event, every extinction caused by a failure to adapt, runs in part on the same phenomenon that lets alpha particles escape from uranium nuclei, the same tunneling from the nucleus of an atom to the nucleus of a cell, from the scale of femtometers to the scale of organisms, from the physics of 1928 to the biology of every living thing on Earth. This is what Gamow and Gurney and Condon discovered. Not a quirk, not a fun fact. The mechanism that makes the universe habitable, the mechanism that has sustained every ecosystem on this planet for 4.5 billion years. The mechanism that may be rewriting your genetic code right now as you listen to this, one proton at a time. The mechanism without which the word biology would have no referent, because there would be nothing alive to study. And it took 4 Nobel Prizes before the physics community fully acknowledged what tunneling does. And none of those prizes went to the people who discovered tunneling. Leo Isaki received the 1973 Nobel Prize in Physics for his discovery of electron tunneling in semiconductors. the tunnel diode. He discovered it in 1957 while working at Tokyo Tsushin Kogyo, which later became Sony. Ivar Gieva shared that prize for tunneling in superconductors. Brian Josephson shared it for predicting the Josephson effect, supercurrent tunneling across a thin insulating barrier. Josephson was 22 when he made the prediction. The Nobel Committee's citation for all three read, "For their experimental discoveries regarding tunneling phenomena in semiconductors and superconductors, respectively, and for his theoretical predictions of the properties of a supercurrent through a tunnel barrier." The word tunneling is right there in the citation. The phenomenon Hund described in 1927 and Gamow and Gurney and Condon applied in 1928 was now a Nobel-winning field. But the discoverers were not mentioned, not in the citation, not in the ceremony, not in the history. Gerd Binnig and Heinrich Rohrer received the 1986 Nobel Prize for the scanning tunneling microscope, which they built at IBM Zurich and first operated on the night of March 16, 1981. The microscope works by bringing an atomically sharp metal tip so close to a surface, within a few angstroms, that electrons tunnel between the tip and the surface. The tunneling current is exponentially sensitive to the distance. By holding the current constant and scanning the tip across the surface, you can map the surface with atomic resolution. You can see individual atoms, not infer them, not calculate them. See them in the sense that the tunneling current traces their positions with a precision of a fraction of an angstrom. This was the instrument that made nanotechnology possible, and it runs on the same physics that a 24-year-old in Göttingen worked out in the summer of 1928. And then in 2025, the Nobel Prize in Physics went to John Clark, Michel Devereux, and John Martinis for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. The Nobel Foundation's press release explicitly cited tunneling, macroscopic tunneling, not particles tunneling through nuclear barriers, but circuits, actual engineered circuits, exhibiting quantum tunneling behavior at scales visible to the naked eye. The qubits in superconducting quantum computers are built from Josephson junctions. Josephson junctions work because of tunneling, the technology that may eventually perform calculations that no classical computer can match. Depends on a phenomenon that Friedrich Hund first noticed in a calculation about molecular energy levels almost a century ago. 4 Nobel Prizes. Not one of them went to Gamow or Gurney or Condon or Hund. The people who discovered the phenomenon that every subsequent prize depended on received nothing. Gamow was alive for the 1973 prize. He could have been recognized. He was not. He was already dead for 5 years. But he could have been recognized earlier. He could have shared a prize for nuclear physics, or for Big Bang cosmology, or for the genetic code. He was passed over every time. The man who explained alpha decay, predicted the cosmic microwave background, and proposed the triplet genetic code never won a Nobel Prize. The committee looked at one of the most creative physicists of the century and decided he had not done enough. There is a pattern here, and the pattern has nothing to do with the quality of the physics. But the implications go further than prizes. They go further than stars. They go further than the technology running in your pocket. They go into territory that I am still not entirely sure how to think about. And I want to be honest about that, because the next thing I need to tell you about tunneling is not about what it does. It is about what it is, or more precisely, about what happens during it. And the answer, or the lack of one, is the part that should keep you up at night. In 1932, just 4 years after Gamow's paper, a mathematician named L.A. McCall asked a question that seems simple and is anything but. When a particle tunnels through a barrier, how long does it spend inside the barrier? How long does the tunneling process take? This seems like the kind of question that should have a straightforward answer. The particle is on one side, then it is on the other side. Surely there is a time interval between those two events. Surely you can define a clock, attach it to the particle, and measure the duration. Surely you cannot. And the reason you cannot is one of the deepest and least discussed problems in quantum mechanics. The problem is that standard quantum mechanics does not assign a trajectory to the particle. There is no path that starts on one side, passes through the interior of the barrier, and emerges on the other side. The question, how did it get through, has no answer in standard quantum mechanics, because the question assumes a trajectory that does not exist. There is probability on this side. There is probability on that side. There is decaying amplitude in between. That is the entire story. Asking how long the particle spends inside the barrier is like asking what color Tuesday smells like. The question applies concepts from one domain to a domain where they have no meaning. But experiments can try to measure it anyway. And for 90 years they did. Different experimental approaches gave different answers. Some measured finite tunneling times. Some measured superluminal tunneling. Particles appearing on the other side of the barrier faster than light could cross the same distance, though without transmitting information faster than light, and therefore without violating relativity. Some measured zero tunneling time. The field was, and in some ways still is, a mess. And then, in 2019, a team led by Satya Sainad at Griffith University in Australia published what is arguably the cleanest measurement to date. They used a technique called the Attoclock, which uses intense circularly polarized laser pulses to ionize atoms and then measures the angular distribution of the ejected electrons with a attosecond resolution. 1 attosecond is 10 to the negative 18 seconds. To give you a sense of that time scale, 1 attosecond is to 1 second as 1 second is to roughly 31.7 billion years, which is more than twice the current age of the universe. That is the clock they were using. A clock so precise that it measures time in units that make a second look like an epoch. Sainad and colleagues performed the Attoclock measurement on atomic hydrogen, the simplest atom, the one where the theoretical predictions are least contaminated by multi-electron effects. Atomic hydrogen has 1 proton and 1 electron. There is no electron-electron interaction to confuse the signal. Every deviation from the expected tunneling behavior must come from the tunneling itself, not from the complexity of the atom. That is why hydrogen is the gold standard. It is the cleanest system you can measure. The experiment works like this. A circularly polarized laser pulse, intense enough to ionize the atom, sweeps around like the hand of a clock. The exact angle at which the electron emerges carries information about when it left the atom, the same way the position of a clock's hand tells you what time it is. If the electron spends time under the barrier, it exits at a slightly different angle than if it tunnels instantaneously. The difference in angle corresponds to a time delay. That is what the Attoclock measures, not the time directly, the angle, and from the angle, the time. Their paper, published in Nature Volume 5, 68, page 75 in 2019, reported an upper bound of 1.8 attoseconds on any tunneling delay. 1.8 attoseconds. For reference, 1.8 attoseconds is the time it takes light to travel roughly 5 angstroms, which is approximately the diameter of a single atom of cesium. In the time it takes light to cross one atom, the tunneling is already over. Or rather, the tunneling never started, because there may have been no duration in which it was happening. And they concluded and I am going to paraphrase carefully here, that the angular offset measured in Attoclock experiments originates entirely from the electron scattering by the long-range Coulomb potential, with no contribution from tunneling time delay. The apparent delays that earlier experiments with heavier atoms like helium and argon had attributed to tunneling were actually caused by the electron interacting with the remaining ionic core after it had already tunneled. The tunneling itself appears to take no measurable time. It may be instantaneous. I still do not know how to think about that. I have read the paper, I have read the theoretical analyses, and I still find it difficult to absorb what it means for a physical process to have no duration. Not a very short duration. No duration. The particle does not experience the barrier. There is no during the tunneling. There is before, and there is after, and in between there is nothing. Not a gap, not a pause, an absence of time that the physics does not fill. I need to pause here because I think the sheer strangeness of this gets lost in the numbers. A particle approaches a barrier. On one side, it exists. On the other side, it exists. In between, inside the barrier, it was never there. Not it was there for a very short time. Not it passed through too quickly to measure. There may be no time interval during which the particle is inside the barrier. The particle is here, and then it is there, and the transition takes no time at all. The barrier is not a place the particle visits. It is a gap in the story, a discontinuity in the narrative of where the particle is, and the narrative resumes on the other side as if the barrier were not there. Now you might be thinking, if particles can tunnel through barriers, what about bigger things? What about you? Could you tunnel through a wall? The answer is technically yes, and practically no. And the gap between those two words is so large that I need to give you a number to make it real. A 70-kilogram person walking at 1 meter per second toward a 10-centimeter thick concrete wall has a quantum tunneling probability of approximately 10 to the power of negative 10 to the power of 35. I need you to understand that number. It is not 10 to the negative 35. That would be small but comprehensible. It is 10 to the negative 10 to the 35th. The exponent itself is 10 to the 35th. That is a 1 followed by 35 zeros. And that entire number is the negative exponent. The probability has that many zeros after the decimal point before you reach the first non-zero digit. To put that in perspective, the number of atoms in the observable universe is roughly 10 to the 80th. The number of Planck times that have elapsed since the Big Bang is roughly 10 to the 62nd. If every atom in the observable universe were a separate version of you, and every one of those yous attempted to walk through a wall every Planck time, and they did this for a duration equal to 10 to the 10 to the 34th copies of the current age of the universe, you would still not expect even a single success. Not one. The wall is safe. You are not walking through it. Not because quantum mechanics says you cannot, because quantum mechanics says the probability is so close to zero that it makes zero look optimistic. The reason macroscopic tunneling does not happen is decoherence. A 70-kilogram human is not a single quantum system. You are roughly 10 to the 28th atoms interacting with each other and with the environment, billions of times per second. Each of those interactions entangles your quantum state with the surrounding air, the floor, the light, the cosmic microwave background. The wave function that would need to maintain coherence across your entire body for all 10 to the 28th atoms to tunnel simultaneously is destroyed instantly by these interactions. Decoherence kills macroscopic tunneling, not by making it impossible in principle, but by making it so absurdly improbable that the word impossible is a reasonable summary. But at the quantum scale, Tunneling is not rare. It is constant. It is happening right now, in the sun, in your phone, in your DNA, in every radioactive atom on Earth. The wall between rare quantum curiosity and the most consequential process in the universe is itself a kind of barrier, and the full story of tunneling has already leaked through it. You just were not told. Now, other groups working with heavier atoms like helium and argon have reported finite tunneling delays of tens of attoseconds. The CNAD result is specific to hydrogen. The heavier atom results may reflect electron-core interactions rather than intrinsic tunneling delay. The question is not settled. I do not want to pretend it is, but the direction of the evidence, at least in the simplest system, is pointing towards something that should make you very uncomfortable. The particle does not spend time under the barrier. It does not experience the barrier. It is simply on one side and then on the other, and the concept of how long may not apply. The man who first observed this phenomenon, Friedrich Hund, saw it in 1927 and lived until 1997. 70 years, he watched the entire 20th century play out. He watched Gamow flee and Condon be persecuted, and Gurney die. He watched 4 Nobel Prizes get awarded for applications of the thing he discovered first. He watched the Attoclock experiments begin to ask whether tunneling even takes time. And he did all of this from a quiet office in Göttingen, largely unrecognized, a ghost in the story of his own discovery. But that is still not the bottom. There is one more level, one more implication, and it is the one that connects the physics to the human story in a way that I did not expect when I started reading about this, and that I am still sitting with. You know what tunneling does to alpha particles. You know what it does to protons in stars. You know what it does to electrons in microscopes and diodes and quantum circuits. But the question nobody likes to ask is what tunneling does to the vacuum itself. In 1977, Sidney Coleman at Harvard published a paper called Fate of the False Vacuum. It is one of those papers that physicists reference casually and non-physicists have never heard of. And the gap between those two groups represents one of the most underreported facts about the universe you live in. Coleman was one of the most brilliant and eccentric theoretical physicists of the second half of the 20th century. He taught a legendary course on quantum field theory at Harvard. He was known for his wit, his clarity, and his ability to take an idea that had been floating around in vague form and nail it to the wall with mathematical precision. That is exactly what he did with the false vacuum. Here is the idea. The vacuum of space is not empty. In quantum field theory, the vacuum is the lowest energy state of all the fields that permeate the universe. The electromagnetic field, the Higgs field, the strong and weak nuclear fields, they all have a vacuum state. And there is no guarantee that the vacuum state we currently live in is the true lowest energy state. It might be a local minimum, a false vacuum. Imagine a ball sitting in a valley. It looks like it is at the bottom, but on the other side of the nearest hill, there is a deeper valley, a truer bottom. And the ball, if it could get over the hill, would roll down into that deeper valley and never come back. In classical physics, the ball stays in the first valley forever, unless something kicks it over the hill. In quantum field theory, the ball can tunnel. The same mechanism, the same exponential leak of probability through a barrier. Coleman showed that if the vacuum is false, a bubble of true vacuum can nucleate spontaneously at any point in space. The bubble wall expands outward at the speed of light. Inside the bubble, the vacuum energy is lower. The laws of physics are different, not slightly different, fundamentally different. The masses of particles, the strengths of forces, the structure of atoms, all of it rewritten by the new vacuum state. The universe inside the bubble would not be a damaged version of our universe. It would be something else entirely. Something that does not include the periodic table as we know it. Something that does not include chemistry. Something that does not include you. Coleman's paper was theoretical. It described what could happen, not what would happen. The question of whether our vacuum is actually false depends on the specific values of physical constants, particularly the masses of the Higgs boson and the top quark. And in 2012, something happened that brought Coleman's theoretical exercise uncomfortably close to reality. CERN measured the mass of the Higgs boson at about 125 gigaelectron volts. The top quark mass had already been measured at about 173 gigaelectron volts. Those two numbers, when fed into the equations of the Standard Model, determine the shape of the Higgs potential, the energy landscape of the Higgs field. And what came out in a canonical calculation by Bertazzo, de Grassi, Giardino, Giudice, Sala, Salvio, and Strumier, published in the Journal of High Energy Physics in 2013, was that the electroweak vacuum, the vacuum we live in, sits on the edge of metastability. It is not clearly stable. It is not clearly unstable. It is in the narrow zone between the two, where the vacuum could in principle tunnel to a lower state. But the expected lifetime of the transition is fantastically long, far longer than the current age of the universe. I want to be precise here, because precision matters, and because the temptation to be dramatic should not overrule the obligation to be accurate. The metastability calculation depends on physics at extremely high energies, near the Planck scale, where we do not have a tested theory. The presence of new physics beyond the Standard Model could change the result. The calculation assumes that the Standard Model is valid all the way up to the Planck energy, which is an assumption, not a fact. Branchina, Messina, and Scher published a paper in Physical Review D in 2015 showing that Planck scale corrections could change the conclusion significantly. The vacuum might be perfectly stable. We do not know. The data puts us in the uncomfortable middle, the ambiguous zone, where the answer depends on physics we have not yet discovered. But the possibility is there, in the equations, published, peer-reviewed, and quietly not discussed in any popular science source you have ever read. The universe could tunnel out of its current state, the same way an alpha particle tunnels out of a nucleus, the same quiet, probabilistic leak through a barrier. And if it happens at the speed of light, which means you would never see it coming, not because you are not looking, because by the time light from the bubble reaches you, you would already be inside it, already gone, already replaced by physics that does not include you. And there is one more thing, one more implication that sits beneath the false vacuum, and is, in its own way, even more personal. Grand unified theories, the theoretical frameworks that attempt to unify the strong, weak, and electromagnetic forces into a single force at extremely high energies, predict that the proton itself is not eternal. Protons can decay, not through ordinary radioactive decay, not through anything that happens at energies we can reach in laboratories, through a process mediated by heavy-gauge bosons, particles called X and Y bosons, that are predicted to exist at energies around 10 to the 15th or 10 to the 16th gigaelectron volts, roughly 1 trillion times higher than what the Large Hadron Collider can produce. At those energies, the distinction between quarks and leptons dissolves. A quark can transform into a lepton. And if a quark inside a proton transforms into a positron, the proton disintegrates. It decays into a positron and a neutral pion. The pion immediately decays into 2 gamma rays. The proton is gone. The atom is gone. The matter is gone. Not because it was unstable in the ordinary sense, because at a deep enough level of the fundamental forces, the walls that separate quarks from leptons are not walls. They are barriers, and barriers can be tunneled through. The proton, the most stable particle in your body, the particle that has existed essentially unchanged since the first microseconds after the Big Bang, could, on a long enough timescale, tunnel apart. The Super Gamow Kande detector in Japan, a tank holding 50,000 tons of ultra-pure water, buried a kilometer underground in the Mozumi mine in the Japanese Alps, has been watching for proton decay since April 1996. The detector is essentially a huge vessel filled with water, surrounded by more than 11,000 photomultiplier tubes the size of beach balls, each one capable of detecting a single photon of Cherenkov radiation. The blue glow produced when a charged particle moves through water faster than light moves through water. If a proton in one of the water molecules decays, the positron and the pion it produces will travel through the water and emit Cherenkov radiation. The photomultipliers will see it. The detector is sensitive enough to notice a single proton dying among the 10 to the 33rd protons in 50,000 tons of water. Using 450 kiloton years of accumulated data from its first 4 operational runs, spanning April 1996 to May 2018, the Super Gamow Kande collaboration set a lower bound on the proton's lifetime. For the decay channel proton to positron plus neutral pion, the lifetime is greater than 2.4 times 10 to the 34th years at 90% confidence. No candidate events, not one, in over 2 decades of watching, over 20 years of staring at 50,000 tons of water, waiting for a single proton to die, and not a single one did. That number, 2.4 times 10 to the 34th years. The universe is about 1.4 times 10 to the 10th years old. The proton's lifetime, if it decays at all, is at least 1 trillion times the current age of the universe. The protons in your body are, on any human timescale, immortal. They were forged in the first second after the Big Bang, and they will outlast every star, every galaxy, every structure in the universe. Long after the last red dwarf has exhausted its hydrogen and gone dark, long after the last white dwarf has cooled to a black dwarf, your protons will still be there, waiting, still intact, still stable, drifting through a universe that has gone dark and cold and empty, with nothing left to interact with, nothing left to build, nothing left to do except exist, and, very occasionally, every 10 to the 34th or 10 to the 41st years, decay. But stable does not mean eternal. It means the barrier is very high and the tunneling probability is very small. And on the time scale of 10 to the 34th years or 10 to the 41st years, or whatever the true lifetime turns out to be, the probability accumulates. The wave function leaks. One by one, over spans of time so vast that the current age of the universe is a rounding error. The protons decay. The atoms they built dissolve. The matter that once formed stars and planets and people and memories dissipates into radiation. Not violently, not catastrophically, quietly. The same way the alpha particle leaves the nucleus. The same way probability leaks through a barrier. The same way everything in this story happens, almost unnoticed. And what you are left with, at the end of deep time, is a universe with no matter in it, just photons and neutrinos and gravitational waves and the fading memory of a universe that once had things in it, things that touched and held and thought and wondered. All of it gone, all of it tunneled away. That is the full implication of what Gamow and Gurney and Condon discovered in the summer of 1928. It is not just that particles can walk through walls. It is that walls are temporary. All walls. The walls of the nucleus, the walls of the Coulomb barrier, the walls of the event horizon, the walls of the vacuum itself. None of them are permanent. They are all barriers. And barriers, in quantum mechanics, are things that probability leaks through. Given enough time, everything escapes. Everything transitions. Everything slips away. The barrier around the uranium nucleus, the barrier between two protons in the sun, the barrier between the two wells of a molecular potential, the barrier of the oxide layer in a flash memory chip, the barrier of the insulating layer in a Josephson junction, the barrier of the hydrogen bond in your DNA, the barrier of the event horizon of a black hole, the barrier of the electroweak vacuum that separates this universe from whatever lies below it. Every single one of these barriers is, in the language of quantum mechanics, a region of exponential decay of the wave function. And in every single case, the wave function does not reach zero. It decays, it weakens, but it leaks through. On the other side, reality continues, different, sometimes unrecognizably different, but continuous. The probability never stops. Gamow understood this at 24. He understood it well enough to write a paper that changed physics, and then he spent the next decade trying to tunnel through a barrier himself, first in a kayak on the Black Sea, then in a kayak near Murmansk, and finally through the polite fiction of a physics conference in Brussels. He made it through. His co-discoverers did not make it through their barriers. Gurney could not tunnel through the political barrier of McCarthyism. Condon could not tunnel through the institutional barrier of HUAC. Hund could not tunnel through the historical barrier of being first but not famous. The physics works, the metaphor works, but the people are not particles. They do not get infinite attempts. They do not have 10 billion years to try again. They get one life, and the barriers they face are real, and the probability of getting through is not always non-zero. I want to come back to the people now, because I promised earlier that the human story and the physics were the same thread running in both directions, and I think you can see it now, but I do not think you can feel it yet. Not fully, because the endings are where the thread tightens. George Gamow escaped through a barrier. He tunneled out of the Soviet Union, and on the other side, in America, he became one of the most productive and creative physicists of the 20th century. He predicted the cosmic microwave background radiation. He proposed that the genetic code operates in triplets. He wrote popular science books that taught generations of amateurs to love physics. He founded the RNA tie club with Watson and Crick and Feynman, and he drew a self-portrait wearing a tie embroidered with the abbreviation for the amino acid alanine. He was funny and brilliant and irresponsible in the way that people who have seen the worst of the world sometimes allow themselves to be. His most famous popular work was the Mr. Tompkins series, which started in 1940. The premise was simple and strange. A bank clerk named C.G.H. Tompkins attends public lectures on physics and then falls asleep and dreams himself into worlds where the physical constants are different. In one dream, the speed of light is 30 kilometers per hour, and Mr. Tompkins watches cyclists undergo length contraction as they ride through the streets. In another, Planck's constant is enormous, and quantum effects are visible at the human scale. Billiard balls tunnel through the cushions. People diffract through doorways. It was physics as fantasy. It was Gamow using narrative to do what equations could not, to make you feel what tunneling looks like from the inside. But Mr. Tompkins lived in a world of playful physics. Gamow lived in the real one. He drank, Increasingly, from the 1950s onward, the drinking alienated colleagues. It strained his marriages. It probably cost him a Nobel Prize. When Arno Penzias and Robert Wilson detected the cosmic microwave background in 1965, confirming Gamow's prediction from the Alpha-Beta Gamow paper of 1948, the Nobel Prize went to Penzias and Wilson in 1978. Not to Gamow, not to Ralph Alpha, his student who had done most of the actual calculation, not to Robert Herman, who had predicted the temperature of the background radiation with remarkable accuracy. Gamow was dead by the time the prize was awarded, but he had been alive when the background was discovered. He had been alive when his prediction was confirmed. And the committee looked past him. He died on August 19, 1968, in Boulder, Colorado, of liver failure linked to chronic alcoholism. He was 64 years old. He is buried in Green Mountain Cemetery in Boulder, under a headstone that does not mention tunneling, does not mention the Big Bang, does not mention the genetic code. The man who explained how particles escape through barriers, who helped explain how the universe began, who helped crack the code of life, is buried under a stone that tells you his name and his dates and nothing else. Condon died in the same city, March 26, 1974. Heart disease. He was 72. After decades of clearance, revocations, and loyalty hearings, and Nixon taking credit for his persecution on the campaign trail, after directing a UFO study that pleased nobody and resolved nothing, after watching his co-discoverer Gurney die in obscurity and his field weaponized and then turned against the people who built it, Edward Condon died in Boulder, Colorado. The same town, the same university system, the same small city at the foot of the Rockies where Gamow drank himself to death 6 years earlier. 2 of the 3 men who explained tunneling ended up in the same city, both destroyed in different ways by the governments they served, both buried in Colorado soil. If you drive from the University of Colorado campus to Green Mountain Cemetery, it takes about 10 minutes. Gamow is there. Condon is in a cemetery in Boulder too. 2 men who independently proved that particles can walk through walls, separated by a 5-year gap in their deaths and a few miles of Colorado highway in their graves. They had not worked together since Princeton in 1928. 40 years of separate careers, separate persecutions, separate descents, and they ended up in the same small city, at the foot of the same mountains. The Condon report on UFOs was published in 1969. Its conclusion was that further study of unidentified flying objects was not likely to produce advances in scientific knowledge. That was the last major public contribution of one of the men who proved that particles walk through walls. He spent the end of his career telling the government that alien spaceships are not real. The government that had accused him of being a security threat trusted him just enough to debunk flying saucers. That was the use they still had for Edward Condon. And Gurney, Ronald Wilfred Gurney, born July 1st, 1898, died April 14th, 1953. He was 54 years old. His obituary in Nature was written by Neville Mott, the man he had collaborated with on electronic processes in ionic crystals. Mott's closing line reads like a eulogy for a man who deserved better. He wrote that it was typical of Gurney that though he could use mathematics as well as another, he never trusted it. No theory was a theory to him until he could grasp it intuitively and, above all, draw diagrams of it. That was who Gurney was. A man who needed to see physics before he could believe it. A man who drew pictures of wave functions and potential barriers because the pictures were, for him, more real than the equations. a man who looked at the alpha particle escaping the nucleus and did not see mathematics. He saw something slipping away. And Hund, Friedrich Hund, born 1896, died March 31st, 1997. 101 years, he held professorships at Rostock, Leipzig, Jena, Frankfurt, and Göttingen. He supervised Carl Friedrich von Weizsäcker, who went on to work on Germany's nuclear program during the war, a fact that added one more layer of irony to a story already saturated with it. The man who discovered tunneling supervised a student who would try to build a bomb that depended on the physics his supervisor had originated. Hund contributed to the development of molecular orbital theory, which is taught in every chemistry department in the world as the Hund-Mulliken approach. Robert Mulliken, who won the 1966 Nobel Prize in Chemistry for molecular orbital theory, said privately that his prize should have been shared with Hund and John Slater. It was not. The Nobel Committee decided that Mulliken had done it alone. Hund's rules, which describe how electrons fill atomic orbitals, bear his name. But the tunneling he discovered first does not. In a 1988 filmed interview with Helmut Rechenberg, asked about the early days of quantum mechanics, Hund spoke at length about Heisenberg and Born and Bohr and Mulliken. He barely mentioned tunneling at all. I have thought about this a lot. Why would a man who discovered one of the most consequential phenomena in physics barely mention it in an interview about his career? Was it modesty? Was it strategic? Was it simply that for Hund, tunneling was one result among many, a feature of the landscape, rather than a monument? Or was it that after 70 years of watching other people get the credit, the discovery no longer felt like his? I do not know. He is not here to ask. He died in Göttingen in 1997, and the University of Göttingen renamed the address of its physics department, Friedrich Hund, Platz 1, in 2004. 7 years after his death, a century and a half after his birth. On that street, students study the physics he originated. Most of them have never heard his name. The man who discovered tunneling first, who lived the longest, who saw everything that happened to everyone else, has a street. Gamow has a crater on the moon. Condon has a lecture series. Gurney has half a law. And Hund has a street in a university town where students walk past his name every day without knowing that the man whose name they are walking on showed them how the sun shines, how atoms decay, how the universe might end, and how long each of those processes takes, all in a single table of numbers published in 1927. Those numbers, that table, that brutal exponential, is the spine of everything in this story. Small barrier, fast tunneling, alpha particles escaping in microseconds. Medium barrier, slow tunneling, protons fusing in the sun over billions of years. Tall barrier, unimaginably slow tunneling, the vacuum holding steady for timescales that make the age of the universe look like a rounding error. Hund saw all of it in one table, in one paper, and nobody told you his name. 3 discoveries, 2 continents, 1 day apart. And the man who saw it first got a street sign. The alpha particle slips away, almost unnoticed. Gurney wrote that. And then Gurney himself slipped away. Condon slipped away. Gamow slipped away. Hund slipped away. One by one, the men who proved that reality does not respect barriers were themselves erased by barriers of politics, of prejudice, of institutional convenience, of historical accident. The physics survived. The people did not. And the tunneling continues, right now, as you listen to this. In the core of the sun, protons are tunneling through the Coulomb barrier at a rate sufficient to convert 4 million tons of mass into energy every second. Every second, 4 million tons. The sun has been doing this for 4.5 billion years, and it has barely used up 1/10 of its hydrogen. It will keep burning for another 5 billion years. Every second of every one of those years, 4 million tons of matter will be converted into light, and every gram of that conversion begins with a tunneling event, a proton on one side of a barrier, a proton on the other side. No trajectory between them, just probability leaking through. Right now, in every flash memory chip in your phone, electrons are tunneling through thin oxide layers to store and erase data. The text you are watching on your screen exists because of tunneling. The device that is showing it to you runs on tunneling. The satellites that transmitted the signal depend on semiconductor devices that exploit tunneling. You are bathing in it. You are built by it. You are reading about it, using it. Right now, inside your own body, protons in the hydrogen bonds of your DNA may be tunneling from one position to another, introducing rare tautomeric shifts that change the base pairing and create mutations. The evolution that produced you may be running at the molecular level on the same mechanism that powers the sun and lets alpha particles escape from nuclei. The same tunneling. From the core of a star to the core of a cell, and somewhere, possibly beyond the cosmic horizon, possibly closer than anyone would want to know, the vacuum of the universe may already be tunneling into a lower energy state, a bubble of true vacuum expanding at the speed of light, rewriting physics as it moves, erasing atoms, erasing stars, erasing memories, erasing the concept of memory. Not into darkness, into something else entirely, something that does not have a word, because it does not have language, because it does not have minds, because it does not have chemistry, because the laws that produced chemistry are gone. The electroweak vacuum sits on the edge of metastability. The calculations are published. The Higgs mass is what it is. The top quark mass is what it is. The numbers go into the equations, and what comes out is a vacuum that might be eternal and might not, and nobody can tell you which. If it happens the way Gurney and Condon described it in 1928, quietly, probabilistically, without violence, without warning, a leak of probability through a barrier, an amplitude decaying exponentially through a forbidden region and emerging non-zero on the other side. The other side, in this case, being a universe with different laws, a universe where the electron has a different mass or does not exist, where the strong force has a different coupling constant or does not bind, where atoms cannot form, where stars cannot ignite, where the word exist has no referent because the physics that produced reference is gone. The universe will not explode. It will not collapse. It will not scream or shudder or announce itself. It will do what the alpha particle does when it escapes the nucleus, what Gamow described in his paper submitted on July 29, 1928, what Gurney and Condon described in their paper submitted one day later, what Hund saw in his calculations a year before either of them, what a young man in a kayak on the Black Sea understood in his bones, but could not achieve in his body. It will slip away, almost unnoticed.